Today I'm presenting this paper, Entangled Polynomial Codes for Secure, Private, and Batch Matrix Multiplication. My name is Qian, a PhD student from USC, and this work is in collaboration with my advisor, Professor Salman Vestini. In modern distributed computing, we face several different challenges. As an example, when we scale up the system, a number of machines could simply fail to return their assigned computation task. These machines are called stragglers, and it's shown that they can significantly prolong the overall computation times, sometimes even lead to a suspension. Secure computation has also become a very popular topic, where the goal is you want to design some algorithms and to guarantee their correctness, even under a scenario where you have a set of malicious workers in your system who may actively manipulate the computation process. In some other systems, you want to guarantee the privacy of your input data set, or even the privacy of your computation task under a set of possibly colluding and curious workers. Coded computing provides a unified framework for solving these problems. In a standard framework, you have an input data set X, which is normally a high-dimensional vector. And the goal is to compute some function g given this input data. The computation is carried out distributedly using a cluster of n workers, where each worker can take a possibly coded version of the input variable and apply a predetermined function f. A fundamental quantity in coded computing to be optimized is called the recovery threshold, which is defined as the number of workers you need to wait in the worst-case scenario in order to recovering the final outputs. This is a quantity that's equivalent to resiliency and security measures in terms of the number of stragglers or number of malicious workers you can handle. The goal is to design these encoding and decoding functions that are used to assign the computation tasks to the workers in order to minimize the recovery threshold given parameters ng and f, and at the same time satisfy other requirements such as privacy constraints. This setting can be viewed as a kind of channel theory type of framework, where you have these coded variables to be sent through some kind of channels that are characterized by the function f to be computed at each worker. And similar to classical communication theory and distributed storage, you want to design these coded variables just like you design coded symbols, using a certain number of workers similar to the communication theory where you have a certain number of channel usage. And in the end, you want to optimize for the recovery threshold, something similar to the communication rate, in order to maximize the amount of tolerance against errors. There are two major differences between coded computing and classical channel theory. Firstly, instead of having a stochastic or combinatorial process, the channel in coded computing is now normally characterized by an algebraic operation. As a consequence, classical coding concepts such as MDS code will no longer guarantee achieving optimal performances. And the key challenge here is how to develop new coding concepts such that after you apply these nonlinear functions on coded variables, the computation results still make sense such that the decoder can use them to recover the final output function. And at the same time, because now we're considering a computing problem, the complexities of encoding and decoding functions become relevant. In particular, among all the codes or all the computing designs with good performance on recovery threshold, we want to focus on a subclass of them, where the encoding and decoding complexities are reasonably low, so they are not creating extra delays in the process. And in many problem scenarios, using linear codes becomes a very natural assumption. To provide optimal computing designs, in one of our earlier works, we proposed a coding framework called polynomial coded computing. The main idea of polynomial computing is to encode the entries of the input variables using a list of jointly designed polynomials such that the composition of the function f to be computed at each worker and those polynomials contains all the information that's needed for recovering the final output. Polynomial coded computing always guarantees achieving a recovery threshold that's no greater than the degree of this composition plus 1. So in the end, you want to carefully design these polynomial functions such that the composed polynomial has a degree that's as small as possible. Taking an illustrating example, we consider a simple coded computing problem where the input variable x consists of two large matrices A and B, and we simply want to compute their product, A transpose times B. Because we're handling big data, we assume that each worker can only store and process a fraction of each input matrix. In particular, given some parameters m and n, we assume both input matrices are partitioned column-wisely into m and n subblocks. The workers each can compute a single submatrix multiplication, where the sizes of the inputs are exactly the sizes of those submatrices. Now, given this formulation, the goal of computing Gx is exactly recovering the collection of all mn possible pairwise products between those submatrices. And if you fix the worker's computation load, one can prove that any computing design would require using at least mn workers, even if no stragglers present. So how does polynomial coded computing solve this problem? It first selects a pair of single-variable polynomials where the coefficients are exactly the subblocks of the input matrices, such that after composing them using submatrix multiplication, the resulting polynomial would have a degree of mn minus 1, where the mn coefficients are exactly the mn submatrix products that we're looking for. Given this polynomial design, if in the encoding phase, each worker can select the distinct evaluation points and take the evaluation of ax and bx as those points as the encoded inputs, then after multiplication, each worker essentially evaluates the composed polynomial at the same point. And as a consequence, if the master or the decoder can collect any subset of such mn evaluations, they can proceed with polynomial interpolation to recover this function hx and consequently recover all the mn products that are needed, which enables achieving a recovery threshold of m times n. This provides a first optimal coding design for nonlinear computing operations. Besides matrix multiplication, polynomial coded computing also provides optimal linear codes for large classes of computing functions, from basic building blocks such as convolution to general computation tasks such as multivariate polynomial evaluations. However, in this work, we would like to focus on one important problem: to compute blockwise partitioned matrix multiplication. And we're going to demonstrate that how by simply using a better computing scheme that's designed for straggler mitigation, you can almost immediately get order-wise improvement compared to all state-of-the-arts for many extended setups, including secure, private, and batch computation. Similar to the matrix multiplication problem we mentioned a few slides earlier, here we want to compute the same function to multiply two large matrices. But in terms of the computation assignment to the workers, now instead of partitioning the input matrices column-wisely, they are instead partitioned block-wise using three parameters, P, M, and N. Each worker still takes a linear combination of the subblocks and compute their product. This formulation enables a more flexible trade-off between resources including computation, storage, and communication. It has also been studied in an Allerton paper by Fahim et al. For straggler mitigation, coding for block-wise partitioned submatrices is relatively well studied, and so far the best-known result is achieved by two subclasses of polynomial coded computing schemes, collectively called entangled polynomial codes. The most significant feature of entangled polynomial codes is that compared to the related works, all of them would require using at least PMN number of workers, where entangled polynomial codes can significantly and order-wisely reduce that requirement down to a fundamental quantity called bilinear complexity, which is order-wise smaller for any sufficiently large parameter values Pm and N, while tolerating as many stragglers as possible. The intuition of the improvement achieved by entangled polynomial codes is based on the fact that instead of using the naive cubic interpretation for matrix multiplication, it builds upon a tensor decomposition technique that has been developed since 1960s, mostly for fast matrix multiplication algorithms. In layman's terms, what this tensor decomposition result says is that in order to multiply two matrices with sizes of n by p and p by n, the total and the minimum number of variable by variable multiplications that are required, which is defined by the quantity bilinear complexity, is order-wise smaller than the cubic formula Pmn for any sufficiently large parameter values. If you do not have any CS background and you just want to get some quick intuition on why this statement makes sense for special cases, taking Strasson's construction for an example. What is missing in this tensor decomposition approach is that it does not provide guarantee on straggler resiliency. And you can even prove a theorem on that. So in order to break the cubic barrier to achieve a recovery threshold that's order-wise smaller than that, we have to design codes that are tailored to this tensor decomposition framework. And such a coding design is provided in entangled polynomial codes, which achieves a recovery threshold that's within a factor of 2 of this fundamental quantity, bilinear complexity. If we're worrying about the cases where the exact value of this bilinear complexity is not yet known, you can always substitute it by any subcubic upper bounds that are guaranteed to exist for any sufficiently large Pm and N. And as a side note, if you compare the computing designs for handling cubic and subcubic decompositions, they have completely different coding structures. So this is definitely not by just plugging in fast matrix multiplication algorithms. As we have mentioned, entangled polynomial codes provide a powerful framework that goes beyond straggler mitigation and enables breaking the cubic barrier with unified coding solutions for several other different settings, including secure, private, and batch matrix multiplication. In particular, in secure distributed computing, you have a setup that's very similar to the basic scenario, except that you have some extra constraints on the encoding functions, such that either one or both of the input matrices are information theoretically private against any subset of at most T coding workers. Now, in private distributed computing, instead of multiplying one single pair of matrices, you want to multiply a matrix A by one of a list of matrices as matrix B, And the goal is instead to keep this index, called query, information theoretically private against any single curious worker. Finally, in batch matrix multiplication, instead of having one single instance of computation task, we want to jointly compute L copies of them in order to exploit possible coding opportunities. Of course, these three problems, they are not completely disjoint. In fact, you can consider all possible subset of mixtures of these requirements and shoot for optimal coding designs for each one of the scenarios. For simplicity, we always assume the amount of computation load you can assign to each worker is one single submatrix multiplication. The problem of finding better coding constructions for block matrix multiplication under these scenarios has been studied in several related works. However, all of them are built upon some qubit-based coding constructions, which would require using at least PMN number of workers for every single instance of computational task, even if no straggler presents. On the other hand, entangled polynomial codes provides unified coding constructions that only requires using at most subcubic number of workers in all cases. Entangled polynomial codes also provide several other properties of practical interest. Firstly, because entangled polynomial codes follows the polynomial coded computing framework, straggler resiliency comes for free in the sense that on top of requiring only a subcubic number of workers, it maintains exactly the same recovery threshold while tolerating as many number of stragglers as possible. And furthermore, in terms of optimality, we can prove that in all possible settings, entangled polynomial codes also fundamentally achieves the optimal recovery threshold within a factor of at most 2. Due to time constraint, I'll focus on two simple illustrating examples to demonstrate how entangled polynomial codes can be adapted to different settings. First, let's take a look at the secure matrix multiplication, where the only additional requirement is to keep the input dataset private against a set of possibly colluding workers. In prior arts, the best known coding solution will always require using at least PMN number of workers, with a penalty due to privacy that requires one additional worker per each colluding worker you need to tolerate, per each input matrix that you need to keep private. Entangled polynomial codes requires using a order-wise smaller number of workers, and in addition achieves the same required penalty for security constraints. The proof consists of two steps. In step 1, we apply the tensor decomposition trick, which converts the problem of matrix multiplication into the problem of evaluating element-wise products of two vectors with lengths that equals the bilinear complexity term. Now, in the second step, we just need to design the optimal codes for computing element-wise products. Recall that when no security requirement is imposed, we have shown in earlier works that the optimal coding design is to interpolate them and encode them using Lagrange polynomials. Now, in order to provide security, one approach is to simply pad these pre-encoded vectors using T uniformly random keys before interpolating them using Lagrange polynomials. One can show that this approach exactly provides the needed security requirements, and it does not interfere with the decodability. In terms of recovery thresholds, note that by adding every single random key, it would exactly increase the degree of the interpolating Lagrange polynomial by 1, which would, as a consequence, also increase the degree of the composed polynomial by 1. Note that we're using exactly T and 2T random keys for one-sided and two-sided security. That exactly achieves the budget we're looking for, and that completes the proof. Now for the second example, how to achieve subcubic recovery thresholds for batch matrix multiplication. The proof is also very simple, consisting of two steps. In step 1, note that when we apply this tensor decomposition trick to matrix multiplication, we in fact never use any one of its algebraic properties, which means the same proof would exactly apply for computing any bilinear functions, which includes the batch computation of L multiplicated products as a special case. So we can simply define the tensor rank for L matrix multiplications and to obtain achievability results for batch multiplication in all possible settings by simply substituting the bilinear complexity with the tensor rank of batch multiplication operation. In the second step, to understand the property of this tensor rank, one can simply apply its subadditivity bound to decouple the parameter L from the expression and arrives at a quantity that is clearly subcubic. That concludes my talk, and thanks for your attention.